All right, this is going to be the key for our homework rational roots, conjugate roots. I'm going to do 2 of these problems. Hopefully that'll be a good start to help you do the other 4. All right, and I will start with problem number 2. So the question asks us to state the possible rational zeros of each function, then use synthetic division to test all of the rational zeros and report which are indeed zeros. And I say watch out for multiplicities. I picked number 2 because this is the only one that actually has multiplicities, and I'll show you what happens and how we can check for that. So, all right, first part, state the possible rational zeros. If something is a rational zero, it must be of the form P over Q, where Q is the possible factors of the leading term's coefficient. In this case, it's 1 and 3. And P are the possible factors of the constant term. In this case, it's just 1. Let's make all of the fractions possible with P and Q. So P over Q could be either 1 over 1, which is just 1, or 1 over 3. And those can be positive or negative because we're dealing with integer factors. So the negative versions of these numbers here also fit in evenly. So let me write that out as a list from least to greatest: -1, -1/3, 1/3, and 1. Those are the 4 rational roots we need to check. All right. It is not possible for a number to be rational, a root of this polynomial, and not be in this list. If there is a rational root, it is in this list. All right, so let's check using synthetic division. I write out my coefficients here. I write out the root that I'm going to check. I'll start by checking -1, and then I add the column, multiply diagonal, add the column, multiply diagonal, and so on. This one gets us a -8. This is not a root. I'll just write a big no. All right, let's check. So I'll write a no. I'll also cross it out in my list here. Little red X there. Let's check the next one. We need that same list of coefficients: 3, -5, 1, 1. This time I'm going to check if -1/3 is a root. Let's add the column 3. 3 times -1/3 would be -1. -6, +2, +3, -1, 0. This is a root. Yes, we got a remainder 0. It means it is a root. I'll put a big check mark over here in my list. Let's keep going. 3, -5, 1, 1. I'm going to check 1/3. See, 3, 1, -4, 4/3, and at this point, where I'm getting these fractions, it's rare that this will recover and become a root. This number here is just not 0. What is it? 16/9. Doesn't matter. This is not a root. We did not get a 0. No, not a root, so cross that out. Let's check our last possibility. 3, -5, 1, 1. I'm going to check 1, 3, 3, -2, -2, -1, -1, 0. So this gets a big check mark. Yes, that's a root. But I've checked everything in my list. I've got 2 roots, but the biggest exponent here is a 3. So I'm expecting 3 roots. Now, they don't all have to be rational, but because of conjugate root theorem, it's not possible to just have one imaginary root. They always come in pairs. Same with complex numbers. We can't have just one complex number root. They always come in pairs. But I need 3 roots. So my only option left is that one of these has to be a double zero. So how do I check to see if 1 is a 0 twice, or if negative 1/3 is a 0 twice? Well, let's just use this row, the bottom row from our synthetic division, and test it with both of these numbers, and we'll see which of them gives us another root, as indicated by giving us the remainder 0 again. So let me check negative 1/3 first. Let's see. Oop, not doing it right. So I'm borrowing the bottom row from this one. It doesn't matter. I could have picked this one. This is a negative 1. That's a negative 3. That's a positive 1. Did I do that right? I thought the other one was our double zero, but it looks like it's negative 1/3 our multiplicity. No, this is 1 mult 2. That one worked, but it wasn't supposed to. How did that happen? Okay, give me a second to look at this. That's a negative 1. We add, multiply, add. That is weird. Let me just, okay. Let me check this with positive 1 again. Let's see, 3, 3, 1, 1, 0. Okay, I figured it out. This is, I said earlier you could check with either. If you're checking for a double zero, you have to check with the bottom row of the synthetic division that gave you the first 0. So of course that gave me another 0 there, because if I've only pulled out this 0, this 1, then that negative 1/3 still remains as a 0. It's only after you pull it out that you can really check to see if it's a double zero. Okay, I feel like I learned a little something there, so that's cool. So now I'm going to check with negative 1/3 again, and it shouldn't work this time. All right, and it does not. Okay. Let's see, that's 9 plus 16/3. Yeah, this is a no, but this is a double zero. So let me make that clear where these numbers came from by putting a note in here that we check for double zeros by using last row again with same root. Okay, hopefully that'll make sense to people who are just looking at the document for this. If I was to write out my roots, let me do that here. I need to write out my roots as negative 1/3 and 1 mult 2. And now I found all 3 of the roots. Okay, and that's for this problem here. I'll make that clear. Okay. I'll say how to write answer. All right, now let's tackle one of the problems in the back. I'm sure plenty of people just came to this video for one of these problems here, since they're some of the hardest problems we've faced all year. Find all zeros. 1 0 has been given. Use conjugate root theorem and long division. So I know that negative 2 plus 4i is a root. Actually, I did an imaginary example in class. Let's do this irrational example here. That way you'll have seen an example of both. All right, I know 1 plus the square root of 17 is a root. Therefore, I'm going to box it. I also know 1 minus the square root of 17 is a root. That's the conjugate root theorem. You write that. All right, to keep going, I'm going to use the two roots that I know to simplify this polynomial. Now I'm going to use them together. Because they're conjugates, they simplify each other really nicely. So x minus 1 plus root 17 and x minus 1 minus the square root of 17 have to be factors. All right, and that's because I can get a factor by just taking a root and subtracting it from x, and I distributed the negative 2 in one step. So x minus root equals factor. Let's distribute this. I'm just going to do it out loud instead of drawing all the arrows. I need to do 9 sets of multiplication here. I do not know that number. All right. X times x, x squared, x times negative 1, negative x, negative square root of 17x, negative x, positive 1, positive root 17, 3 more to go, positive root 17x, negative square root of 17, and then our last term is square root of 17 times a negative square root of 17. That's going to be a negative square root of 17 squared, because it's square root times square root. So if you multiply anything by itself, you can write it with a squared. And the square root and the squared cancel each other out. And this just becomes a minus 17. Okay, I'm going to write that again, just make it super clear where this 17 came from. Square root of 17 times negative square root of 17 equals negative square root of 17 squared. Those cancel out. That's where it comes from. All right, let's simplify this down. We get x squared minus 2x. Boom. These terms here cancel, these terms here cancel, and 1 minus 17 is going to be a minus 16. All right, so this quadratic is a factor of this quintic. Let's use it in long division to simplify our quintic polynomial down to something that's just cubic, and we'll be able to solve it. So I got to copy it down. All right, I ask myself, x squared times what equals x to the 5th? That's an x to the 3rd. Then I multiply that x to the 3rd to each of these 3 terms and then write it below my polynomial. X to the 5th minus 2x to the 4th minus 16x cubed. I'll subtract that away. I get negative 11x to the 4th plus 21x cubed. Drop down another term and repeat. Yep. Okay, what do I have to multiply x squared by to get a negative 11x to the 4th? Well, that's a negative 11x squared. Do the multiplication, negative 11x to the 4th, 22x to the 3rd, 16 times 11, I feel like I should know that, is 176. subtract it away. Parentheses, very helpful to making sure you do the subtraction right. If you make a mistake in this problem, it's not because you didn't understand the problem. Like 9 times out of 10, it's because you added 2 numbers wrong. And it's really frustrating because you did everything else right, and then at one point you added instead of subtracted. So we'll just be super careful when doing this subtraction that we do it correctly. I'm using a calculator instead of trying to do the harder steps in my head. Drop another term down. Let's see, this is going to be x squared times a negative x will give us a negative x to the third. Multiply it to each of those terms. Draw a line, parentheses, subtract, and those cancel. 13 minus 2 is 11x squared. Negative 6 minus 16 is a negative 22. Just wanted to be extra sure. We drop down our last term, a minus 176. And I need my final term here is going to be plus 11. Finishing out the long division is just a way to double check your work. So 11x squared minus 22x minus 176. Subtract that away. Remainder of 0. Let me take this right off the top, bring it over here. And now I've got my simplified cubic. That's going to be, we're going to be able to solve this with factoring by grouping. You can already see what I want to pull out now. Let's create our groups. The greatest common factor here is an x squared, leaving behind an x minus 11. We can pull out a negative 1 here, leaving behind an x minus 11. Regroup. This becomes an x squared minus 1 and an x minus 11. Zero product property. I set these individually equal to 0 and solve. I get x equals 11 as my third root. And after I take the square root here, x squared equals 1, square root. X equals the square root of 1 is 1 and negative 1. It's plus or minus 1. So we get 2 more roots for a total of 5 roots. I think that does that for this problem. Maybe I'll just double check that we got the right ones. 1, negative 1, 11. 1, negative 1, 11, and then there's our 2 conjugate roots. Okay, all right, I'll end the video here, and good luck with this homework.